Hello everyone, it's February the 2nd. I wasn't able to do this yesterday, so I have to do it today, and I'm actually not sure if I can do another one later tonight. But anyway, we are going to handle this one first. So the plan is we're gonna do the challenge for today, definitely, and after that, after the challenge for today, what we're gonna do is we're gonna go back to the groups of strings. Now the problem from the contest last week. Yesterday we had a solution. If I can take a look, yes, we had a solution yesterday for group of strings, and it was all right. Right? It was all right. We convert words to bitmap, and that's that. But it was slow. Right? It was very slow. 8,000 milliseconds. So the better ideal is, and we're still going to build the graph like this, but as we are building the graph, we're going to use union find, right? Union find. So eventually, we just need to count union find. So that will be a better solution. But anyway, let's first take a look at the things we're going to do today. I think this is an old problem. I solved it before. Oh, hold on. Do not show me. Do not show me. Wait, how do I do this? Result of default. Confirm. Yep. Okay. Pretend I didn't see it. Well, I actually didn't see it. All right. Given two strings, S and P, return an array of all the start indices of P, S anagrams in S. An array of all the start indices of P's anagrams in S. Okay, so 0, and 0, 1, 2, 3, 4, 5, 6, BAC. I see. Anagram is a word or phrase from by rearranging the letters of different word or phrase, typically using the original letters exactly. What do you mean by typically using this? You can only use it exactly once, right? So AB, BA, okay, nice. SMP, SMP consists of lowercase English letters only. Okay, so what do you think? So what we want is a substring that conforms to this, right? And because it's an anagram, it can only be 3. So the first idea in my head is a sliding window, right? If we get 3, we evaluate if it's good or bad, and if it's good, we move forward, right? We move forward, and we move forward. Okay, yeah, that's So the only difficult part, I mean, maybe it's possible just to, no, it's not possible to compare because in an anagram. So what we're going to do is we can set a counter, right? We set up a counter, we do this, we do a counter, and every time we just pop 1, we add 1, we pop 1 and add 1. How do we know it is the same as this? That's a good question. How do we know if it's the same? I mean, we can do a counter comparison, but that will take on to run. Can we figure out a way that will be easier to, I mean, to be honest, if it's a counter and every time we pop, we just, can we do better? Can we do better than a counter? I think counter probably is my, because I submitted 2 methods, right? The first method probably is the counter, but it's slow, right? It's slow. If we can find a better method, that will be nice. I mean, what we can do is, let's see. Yeah, if we find all the positions, that won't be too nice. Counter. I mean, we can just compare counters. We can do that. We can compare counter, but that's 26, right? We only need to compare 26. Huh. might as well compare arrays, right? We just do array. What are you doing, man? I'm gonna copy. So for today, alrighty. So here is what we want. We want to not a counter. We're just gonna go an array. We can call it counter. It's fine, but it's gonna be 0, right? Times 26, right? So what we're gonna do is produce the counter first. Well, actually, we can just say for letter in S, right? S. We can do a target, right? Shall equal to also 0 times 26, and then for letter in P, I would say target ord letter minus 97. Yeah, I believe it's 97 minus 97 plus equal 1, right? And then for letter in S, what we're gonna do is we're gonna take the first. I can do like this, right? For hold on. We can say for I in enumerate P, right? So I have this, and I have counter. That's gonna be ord si, right, minus 97 plus equal 1, right? And then what we're gonna do is for the new one, right? Every time we go for the new one, we compare the previous one, and if it does, we just add, and then we do the new one. Yeah, so we have the new one, and we compare the previous, and then we change it. The new one, but in that case, we won't be able to evaluate the last one. Therefore, what we can do is we're going to have a result, right? Result res will equal to, yeah, we can say res equal to len p. No, with a start, so it'll be 0, right? If counter is equal to target, else this, right? So then we can say, actually going to be for I in range len p, right? Because p is always smaller. Oh, actually, huh? P is not. It didn't say p is smaller than s. P could be larger, right? If p is larger, if p is smaller than s, this one works. If p is larger, then this one doesn't work, which means we should just get, let's say SMP. How about this? SMP is len s and len p, right? I would say if s is smaller than p, then it's impossible, right? We just return empty, empty. Otherwise, we can do this, and from len p, which basically is s, right? No, not s, p, all the way to s. Okay, so that's that. So every time we get a new one, so we say counter, right? Old one minus equal 1, and then counter new one plus equal 1, right? Minus plus, and the result counter, we say if counter is equal to target, then rest.append I minus p, right? So we add this, we remove this. If I, so I currently is p, and I minus p will be 0, so it has to be plus 1, right? Plus 1. And then we return rest at the end. So all we need to do is handle this. So the old one we give away is going to be s I minus p, right? I minus p, but we have to go ord this, right? Ord, no, hold on, it's going to be this. Ord this minus 97, right? And this is the new one we just add in. So it's ord si minus 97. Okay, let's run the test cases. So we have, this is the first test case. This one shall return 0 and 6. Okay. Well, the second one is this shall return 0, 1, 2. Okay, this one shall return 0, 1, and 2. Okay, 0, 1, and 2, and of course we have to remove this stupid part. Okay, this can be SMP, and this is fine anagram, SMP. Okay, run it. Oh, shoot. Ay. I don't know why I did that. I think that's the only two parts. So it would be these parentheses, man. Parentheses. So this one is a parentheses. This is also parentheses. Yep. Right, let's see how fast this one runs. You want other test cases? Let's run some test cases. It's fine. Let's run some test cases. How about these two? But we change the order, right? That's one thing we can do. We change the order. And of course, A and A and B, right? And of course, A, and then we have A, like something like this. Okay. Yeah, some test cases that I think will be necessary. Looks good. All right, we'll submit this. And it passed with a, it's the same runtime as before. Same runtime as before. We can take a look at what we got, why it is so good in the last time. So this one is 438, right? So sliding window with a counter. When we run at 212 milliseconds and the 34% ranking. All right, so we're gonna take a look at this one, and of course take a look at this one. They might have changed the test case, which is possible. Okay, 61 test cases. 61 test cases. No, this one's better. All right, take a look. Then use sliding window to keep track. That's exactly what I did. That's exactly what I did. If this append, this, if this smaller than, yeah, that's exactly the same, right? That's no, not exactly the same. It's almost the same. I have the same here, and I build up the two things. That's the same. And this is the only part that's slightly different because I think I was counting from the start. Yeah, I was counting from the start. And I'm gonna add this. And once it was I plus m is smaller than, then I don't even know what s count gonna plus equal to 1. I plus m. Yeah, it makes sense. Yeah, this is basically the same. Yeah, it's the same. So I suspect the difference in the runtime is they might produce a larger test case. That could be a reason. But also be interesting to check this solution. I think this probably is counter. And I have to handle the counter, like add and delete. Right? Did I use the counter for this? Yeah, I use the counter for this. I have to delete, which is. Oh, I just read this is only done. This was 3 weeks ago. Wait, what? Oh yeah, this was done 3 weeks ago from me. Ah. All right. Anyway, so we handled this. Let's go to group of strings. We're gonna go bitmask, but union find. So what we're gonna do is do union find. Okay, union find. I still cannot write union find myself. Therefore, we need to say snippet union find. Yeah. Okay, let's do union find. Okay, that's union find. So we should do solution 2. This solution 1, and we shall have a solution 2. Same idea to build up the graph, but we use union find to quickly identify which words form a group. All right, so convert to bitmap. That's the same thing, and every time. So here. So instead of doing this, right? We can just say disjoint DSU disjoint unit equals DSU. All right. What do we need? We need n the size. What is our size? How many do we have? We have n number of words, right? And then this is fine. Remove one letter. One position add. We need to do that. And this is bitmap. Do we need that? We do, right? We do. When a union, the union will be indices, right? When the union, the indices. So how do we do that? We can say bitmap.get, right? Hold on. For BM, that's a bitmap, and then we have all the indices, right? And then we simply just get the first one. Yes, get the first one, and we say for J in, right? For J in bitmap.get this. For J in this, DSU dot union, right? What we call our union just x and y. So dot union bitmap this 0 and J. Okay. So that's that, and we do the exact same thing for here, and that's or, and then we still union this, okay, And once we're done, hold on, one more thing. So we're gonna do here, same thing for J, but this one will be different. It'll be this, right? And then we also do this. Once we've done all that, we're gonna just say for J, right, in bitmap bm bm 1 to the end, right? 1 to the end. We say dsu.union bitmap this and what? And J, right? I can actually do index equal to, so I don't have to do this so many times. Right, these shall be index right here, right? So once we're done, right, once we're done with everything, we will have the DSU. So we just look into the DSU, right? We just look inside DSU, but we need to compress. Should we compress the path? We might need to compress the path. That's a good question. Shall we compress the path, or has the path already been compressed enough? Well, every time we find, right? I think we have compressed enough. All right, so we're just gonna go with the pair, right? We're gonna do the self.pair. So we're just gonna do a counter, right? Do a counter because everybody shall be compressed. Maybe just do one more time. Do one more time for good measure. For hold on, maybe we have done. Have we done enough? I think I have done enough. So what we do is counter the par and return, right? Return the number and then return the max. That's what we want. All right, so we're gonna say counter equals counter dsu dot par, and we're gonna return a len counter, that's the number of groups, and a max counter dot values. Okay, let's try this. That is so slow. What happened? What happened? 7 seconds. And this is not correct. Huh. You saying we do have to compress? Yeah, this seems to me that like we do have to compress. Wait, hold on. The number of groups is also not the same. Okay, how about we compress? I range n dsu.find I. Does it want to return anything? Fine, return the parents. Okay, run again. Yeah, we do have to compress again. So must compress path again. Okay, this is my second solution. No, I'm actually not sure if this one will run any faster. Last time it's 8 milliseconds. 8,000 milliseconds. Okay, submit. Six. 6,000. 6,000. Still not fast enough, but it's better. So this one we run. We call it O1 login, right? Yeah. We call it O1 login with 6640 milliseconds. This is the login, the smaller actually than the giant constant. 5% ranking. Where is the O1 login? I don't know. All right, let's go back to discussion. So that's the fastest I can get. So I have this, and I have union find. Okay. Language dependent evaluation. Bitmask. Only consider delete operations. Okay, what he says. Yeah, this is the, I think, alright. Move from one word and get another. Or keep each word as spacebar. Yeah, okay, that letter is the same, yeah. Do it in a stupid way. And hold on, what's the size of each word? Maybe that's why I'm going so slow. No, size of each word is 26. Size of each word is 26. My way, I'm picking all the, my way is fine. What is this way? Apple, 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 apple. Then two words from our list which have the same mask need to be connected. N times D. Oh, I didn't understand. So I create this mask, right? Then two words from our list. two words from our list which have the same mask. Oh, yeah, two words from our list which have the same mask need to be connected. That's true. If they have the same mask, which means you can. It's expensive to keep such mask. We denote star by 1 left shift 26. Save it as number as well. Then we denote, then when we connect graph, for each mask it is enough to connect only adjacent elements. Say we have 312. What does this mean? For each mask, it is enough to connect only adjacent elements. I don't understand. Yeah, I don't want to read into that. I just want to understand this part. What do you mean by one? What's this 312? What's this? Oh, that's a word. I think that's a word. Right? And now I have 1. What's 29? It is expensive. It is expensive to keep such math. So we go further. We denote star by 1 left to 26 and save it as a number as well. Then we connect graph for each. Okay, so we say we have all these graphs and each one is denoted by a value. And save it as a number. I mean, it's just position, right? So we can have the original value and we set this to unknown. So we say this, hold on. How do we do this mapping? Okay, this is all the bitmap. I think this is the same. We have the same idea here. Masks. We enumerate a word. Okay, we go for word by word. And the values. What's the values? Word I minus word A for I. So each word, I got a value for each word. And the mask, the current mask, sum 1 for I. Okay, this is the same as this. So we get the mask for each word, and for eigenvalues. So eigenvalues, we say mask minus this plus this masks this append index. What is this? One left shift this is the position, right? So we delete this. So at each position, right, at each position, each value position, we say we can remove this is remove, right? And I add one value. I remove one and I add one. And this is a remove. Yeah, this is a remove. It is not an M. Continue. Otherwise, we do this. I think G is the adjacency list. So G index, which is the current index, plus equal to this is thinking there is no repetition in the word. How? What if I have repeats? You'll be missing. Anyway, so I just this plus. I understand this, but I don't understand. What does this one do? Masks. It just says anyone with this mask can be formed together. I think that's what it means. So we remove this, so we don't have this, but we can have something else. And that something else could be anything else. So I just need to remove a letter, okay, and add something to the front. So this is like a signature, which means in this, I don't have this, but I can have anything else. Right? I can have anything else. So we add this into the masks. I see what you did there. Now I understand. Okay. Yeah, it might be an easier way, which just means we're gonna have to change here. So we have the bitmap, right? We have the bitmap, and it's this part we can simplify. How about add one letter? They never consider add one letter. They only consider minus a letter. Hold up. If add one letter, right? If I add letters, then that's the same as the other one minus a letter. Oh my god, yes, that's why you only need to consider, which means we only need to remove, we don't have to add. Ah, that is true. So we don't have to do this. Well, I mean, in my case, I just don't need to do this, but I do have to go because this is my way of handling this. Yeah, I mean, I don't think it's going to be significantly faster, but so the update is update. We don't have to consider minus a letter because no, we don't have to consider add a letter because adding a letter for the current word is equivalent to minus a letter for the other word. Thus, considering minus letter is sufficient. Maybe let's try it. Let's see how fast this one runs. Doesn't seem to be significantly faster. Ooh, the hell. Oh, and also very fragile. Interesting. It failed. How did adding it? I think it's borderline. This one just borderline. Let's try the other methods. Let's try this method, right? This is actually not too bad, but I think it's the same. Like, how is it different? Well, let me run this one more time. How could this be slower? So, look, the same method, right? Same method. One is time is TLE, and the other time is 6,000 milliseconds. But still, the same idea. I don't think there's any saving though. Right? He does the mask here, and he has to do this part. This part, God knows how long it's gonna take. And I'm doing replacement here, which is anyway. Let's see. Yeah, bitmask. Oh, this is not, this is n times 26 times 26. It is barely passing. So for each word, what's dt? Okay, this is my bitmap, right? And I always say if it's in dt, and my I is going to be dtx. The hell is dt? This, if, that's a 1, y, will turn to 0. If y is in this, dt y, and dty equals I. And dtx equals I. That's the father, right? So-called. We find the index of the first word with bitmask x. If I is the father of I, which we'll use for union find. No, that's the union find. Hold on, let me see again. What is dt? I don't know. That's just a dictionary, right? I think that's just mean a dictionary. If x is in the dictionary, x is my current, right? X is my current pattern. And we say if my current pattern is inside, then we union. Okay, so this is the pattern, which is what is the last index who has this pattern. Okay, yes, this I make sense. I know what this one does. If two words are connected by replacement, they have same child after deleting one letter. Hold on. If two words are connected by replacement, what does replacement mean? We just replace one letter, right? So everything else is the same and one letter is different. So we say if they're connected this way, then they have the same child after deleting one letter. So if we delete one letter and the other one deleting one letter, they do have the same child. That is true. So I go through 26 letters and we find the one that's a 1, yes. And we find the one that's deleting, so I delete that, right? I delete that. Then I look inside. I look inside the dictionary and anything that has, because I delete that, right? And if you delete something resulting in the same, then we can, so I can union these two. And after that, I update to I. Why do I update to I? I don't think you need to update to I. It could be the old thing. Because with union find, you have to find eventually. I think I understand. This is really good. This is really, really good. Okay, so solution number 3. All right, solution number 3. So basically, what we want DSU, we want this. These are just regular things we need. But on top of that, right? Let's see if we can write it without looking. Okay. So on top of that, so the idea. Let me write the idea. So this is from comment in Lee215's solution. Yeah, I like this one a lot. It's clean and clear. I don't want to see it. Okay, so the idea is the idea is to remove, right? To remove a letter from So given a word, we remove each and every letter. After a letter is removed, right? After the letter is removed, we have a new bitmask. If we have recorded the previous letter, the previous word that also has a bitmask, also has the same bitmask. Either after removing a letter, right? Removing a letter, or not removing any letters, then the two words shall be unioned, right? And the two words shall be unioned. Now this is the key. When the current word removes a letter and it matches, right? It matches with some other word without having to remove a letter. This is apparently valid. On the other hand, if the current word removes a letter and it matches with some other word that also removes a letter, also removes a letter, then these two words also are connected because they differ by only one letter. Wow, that is the epiphany. This can significantly reduce the time to find connections between replacement. Okay, so what we want here, we have these two, and then we just need a mask dict, right? That's going to be what is that going to be? That is going to be just a dictionary, right? So this will just record. I'll say record the first letter, the first word, the index of the first word that has, right, first word that shows a certain bitmask. Record the index of the first word that show. Okay. So now we just can go for I word in enumerate, right? When they enumerate, I think I spelled it wrong. Enumerate words. Okay, so what do? We're going to enumerate them, right? And so for each one, we're going to first create a mask. So the mask shall be a sum of for letter in word, right? I'm going to go 1, left shift something, right? What do we left shift? Or letter. I always use this, or letter minus 97, right? For letter. So this is the mask for the current word. And if if mask is in mask dictionary, which means we have something before who is exactly the same as me. So that I have to do. So I say dsu dot union I and mask dict mask, right? So it's there has been repeats. There have been repeats. Okay, next one, right? We're gonna remove when you say for I, now for j in range 26, right? And we say if mask right shift j, and we'll have to do this. Actually, don't. No, we don't have to because this executes first. And 1, right? So the j's position is good. Then we say remove mask equal to mask exclusive or, right? Mask exclusive or 1 left shift j, right? So this is the new mask, right? And then we say same thing. If remove mask is in mask dict, so whatever is in it, we need to dsu dot union current I and a mask dict remove mask, right? So yeah, so we do this, we get every single one. Once we've done everything, we're gonna say mask dict mask equals j, no equals I. So once we're done, we compress one more time and we return the result. So this is remove, right? Remove a letter. So this is solution 3. I run it. It's not correct. But it's very, very fast. Unfortunately, it's not correct. Why? This is fine. So the only difference is, I think the only difference between the writing, this is all the same. This is also the same. This is the same. This is the same. This is the same. Unless I remember wrong that the precedence I got it wrong. But I don't think so. Yeah, it's not a precedence. I remember the precedence correctly. So this the union. The only difference is this. This is the only difference, which means we got a y, which is this remove mask, and we assign the remove mask to the current. And let's do that, and then so we say mask dict remove mask is equal to j, no, equal to I, and then we run it. Then we freaking pass. Why is this line important? What does this line do? Oh, I see. Because I need to set the remove mask. Because if I don't set the remove mask will never be there. Right? So we need to set something down. Yeah, this is just to set the remove mask. Yeah, set the... Well, we can actually say else, right? If it's in, then we do this. Otherwise, we need a set, right? And then we can do this one up there as well. If it's in, then we do this else. If it's not in, then we do this. And oh no, and we run, and it pass. Yeah, this makes more sense to me. This makes more sense to me. Remove letter. This is the key step. key step. Yeah, I think this one shall score really, really well. Holy guacamole. This one's so good. Nice. Yep. 3,000. This one's so good. This one's so good. If two are connected by replacement, they have the same child after deleting one letter. Wow. Wow. I am speechless. Absolutely speechless. Absolutely gorgeous. Gorgeous solution. Yeah, I mean, if you need to use union find, you need to be able to write this. I am not able to write this. This is the rank. The rank is not equal. Or rank plus equal 1. Yeah, that's fine. Doesn't matter. We have to use a counter anyway. I like to use a counter. Yeah, it's easier. Counter is easier. Woo-wee. All right. That is it. That is it. All right. So, good problem. Very, very good problem. I need to like this problem. I did solve it myself, so it's not really a nightmare. I got the idea, but this is just good. Can I add to a list? Yeah, it's not a nightmare, but it's a good problem. It's a very, very good problem. All right, I will see you guys soon.